Lab 5, Falling Spring. The main purpose is to apply Newton's laws of motion to the real world. The experiment today involves the motion of a stretched out Slinky dropped from rest. We'll be measuring its motion and create a model to determine why the bottom of the Slinky remains in the same position for a period of time. We'll be using the net force principle. Now on to our observations. We have our Slinky video loaded into Tracker. The origin is defined at the top of the Slinky, and the Slinky is being dropped in the negative y direction. We take this data created by Tracker to create our computational model. First, we have to make a few assumptions. For one, the system is a Slinky, mass, and Earth. The mass of the object is 0.05 kilograms. Our initial position from Tracker is 0, negative 1.809 meters, and our initial velocity is 0 as it's dropped from rest. Change of time is 4.029 seconds. Now, for the computational model, we first initialize the ball's mass, initialize the vectors from our assumptions, and then start our t variable and initialize it. We take our acceleration due to gravity, which is 9.8 meters per second squared, and then our j-hat vector, and a proportionality constant for the magnitude, which we define as 2.6. Then we start this initial while loop for when the bottom of the Slinky is remaining at rest. We calculate the weight force and the tension force, and since these are both equal to each other, they cancel out and our F net is 0. We plug this using the momentum principle and calculate the velocity, and then the position update formula to calculate the position. Then we advance the clock. Then we create the second while loop, which iterates up to 4.029 seconds, which is the time of our Tracker video. Then calculate our weight force, and then this time our drag force, which is the drag force due to the air. And we calculate our F net, which is our weight force plus our drag force, and then we're able to use the momentum principle and position update formula again to calculate those two components. Then we have our computational model, and as you can see, it does closely resemble our video from Tracker. We can take this data created by the computational model and use it to compare to our observations. As you can see, the two graphs align pretty close to each other, the orange being the model and the blue being the observations. Although you can see a slight discrepancy, this can be due to two reasons. For one, there could be additional forces not accounted for. For example, another force that we didn't include that could be experienced at the top of the Slinky, and as we've only counted for the bottom of the Slinky. This could be adjusted with including that additional force. Additionally, the errors from Tracker from manually marking the Tracker data in the Tracker software could have caused some issues. This could be adjusted by lengthening the amount of frames in the video, as this was 30 frames per second. Using 60 frames per second could allow for more accuracy for the future. Now we have a model of Professor Fenton, who acquired the drip in this video, and we have a more updated model where Professor Fenton becomes the drip king.